everyone. My name is Kelly Hao. I am an assistant professor from Georgia Tech. Today is my great honor to talk about our work, software hardware co-design for memory-efficient, low-latency personalized PageRank. This is the outline. So first, I will briefly introduce what is personalized PageRank, PPR, and then introduce our approach, MeLoPPR, which is memory-efficient and low-latency. And third, I will introduce our FPGA-based accelerator, and finally comes with the conclusion and future work. So first question, what is personalized PageRank? Originally, PageRank evaluates the importance of the page nodes within a web graph. So personalized PageRank means there is only one source node. For example, in this figure, there's only one node S. And we are computing the importance of all the other nodes related to this source node S. Random walk is a typical method used to solve this PPR problem. And as its name indicates, there is an imaginary robot that starts from the source node S and proceeds for total L steps. In this case, L equals 4. So this is the first path the random walk takes, and this can be the second path. Finally, the random walk will take a lot of iterations, and then the algorithm will sum up the number of visits for each node. And sometimes at each step, there is a probability, we call it alpha, that this robot can jump back to the source node. In this case, we call it alpha decay random walk. And in our algorithm, we also care about this alpha decay. So finally, the PPR is actually computing a probability distribution of these nodes. We call it PPR scores. The larger probability, the higher PPR score means this is more related to source node S. And typically, we only care about the top K most important nodes. This is because PPR is also used for personalized product, news, social account recommendations, and in reality, we only care about the top K most important matches. And alternatively, PPR can also be computed by this graph diffusion algorithm. Here are some terminologies. We have a graph G, and we have its adjacency matrix A, and we have its diagonal matrix of degrees D. And we have a random walk transition matrix that can be computed from A and D. And we also have two PPR vectors, S0 and SL. These vectors store the PPR scores. So S0 is the initial PPR score vector, and SL is the final PPR score vector after total L steps. And here, SL can be computed using alpha, S0, and this transition matrix W iteratively using this equation. And we call this procedure graph diffusion, and we denote it by GD, meaning it starts from initial vector S0, and after L steps, we get this final PPR vector SL. And note that in this initial vector, there is only one node whose value is not 0, because this is a personalized PageRank and there is only one single source node. And in the final SL PPR vector, we pick up the top K nodes with high scores. So in this example, K equals 3. And this formula is the formal definition of graph diffusion computation, and we will still use this formula later. So this is how we compute PPR using graph diffusion. What is the challenge here? The biggest challenge here is the large graph size. We all know that a real-life graph can be very large, can be up to several gigabytes, and there's no way to fit into an edge device. So here we're targeting edge device for security and privacy consideration. For example, sometimes you have some personal information you do not want to share with the cloud, but still want to know your own recommendation. So this is the first challenge. This is a challenge that the graph size is really huge. Even though we're just computing the subgraph with depth L, large L, it still can be very large because, especially when your graph is densely connected. So this is still a big problem. So in order to solve this challenge, the first contribution of our work is we want the PPR to be memory efficient, so it can be executed on edge devices for privacy and security consideration. And second, we also want this PPR to be low latency because we want to shorten the response time and improve the user experience. So this is the main idea of MeLoPPR. It is essentially a multi-stage approach. that given this large L, we want to break this large L into a sequence of smaller L's, L1 and L2, such that large L is the summation of them. And in this case, we compute MeLoPPR, we compute graph diffusion on these subgraphs. So we can see that in this case, after breaking, the required subgraph to compute is much smaller than the original one. We can compare with this yellow subgraph with this large gray one. So the required subgraph is much smaller, which is really memory efficient. And this can be achieved through stage and linear decomposition, which will be introduced shortly. And also we can exploit the sparsity of these subgraphs, that we want to compute these subgraphs only when necessary and skip most of them to achieve low latency. Now let's take a look at the stage decomposition first. So this is the original graph diffusion definition. Let's ignore the details, but the first term can be reorganized like this. And the second term can be similarly reorganized in this way. They're both using the original definition. And if we do the substitution and we clear out other terms, you may already notice that actually this is the stage 1 computation, and this is the stage 2 of graph diffusion. So this is the cleaned formulation, and we can see that this is actually computing stage 1 graph diffusion, and this is computing stage 2 graph diffusion. So apparently for stage 1, it requires a smaller subgraph with depth as L1. But what about stage 2? Actually, because of this initial vector of L2, it still requires the whole subgraph, like this blue graph indicates. So you might ask, so what's the point? The memory is not saved so far. So fortunately, we have the second weapon that we can utilize called linear decomposition. Let's take a look at this initial vector of stage 2. This vector can be written as a summation of different vectors, where in each vector there is only one value that is not 0. You may find this familiar to you because this is actually another graph diffusion on a smaller subgraph. For example, here, for the first vector, this is actually computing graph diffusion on this subgraph. And for the second vector, this is actually computing the graph diffusion on this subgraph. So in this case, we can regard the graph diffusion of the second stage as a combination of a graph diffusion over all non-zero elements. But in this case, it requires much smaller graph size. So in this case, if we do this linear decomposition, all the stages can be computed using only smaller subgraphs, which is really memory efficient. But you may already notice that it might be time consuming to compute over all non-zero elements, because if you have thousands of non-zero elements, you have to run thousands of graph diffusions, which can be really time consuming. So how can we solve this problem? The answer is very simple. We have a third weapon, which is called PPR vector sparsity. So luckily, we can notice that the initial vector of stage 2 is actually very sparse. So in this figure, I'm showing the histogram of the PPR vector after stage 1, the initial vector of stage 2. This is in log scale. So we can see that actually there is only less than 1% of the node have relatively large PPR scores, and more than 90% of the node have close to 0 scores. So this allows us to selectively choose next stage nodes with larger scores. Let's see whether this sparsity is indeed beneficial. In this case, I'm showing some example using 3 real-world examples to demonstrate. So first, we are computing only 1% of the next stage nodes, and we already reach a precision higher than 70%. And then we compute 2%, 3%, and 5%. And after computing 5% of the next stage nodes, we already reach a precision more than 85%. And finally, if we compute 30% of the total nodes, the precision is already higher than 95%. So this is indeed showing that using the sparsity, we can skip a lot of redundant nodes. So this is the overall of the MeLoPPR, how we achieve memory efficient and how we achieve low latency. Now let's introduce our FPGA-based accelerator. So this figure shows the basic architecture of the accelerator. There are two parts, CPU part and FPGA part. So inevitably, we have to subtract the subgraphs using BFS algorithm. So this part is done on CPU, and the CPU is sending the subgraphs to PL side. And the PL on FPGA, it is storing the subgraphs on chip and then apply the graph diffusion, and finally it has to integrate the scores into a global score table to maintain the correctness. So in this case, in this sample, I'm showing two processing elements for graph diffusion. There are two PEs, but in reality, we can increase the number of PEs and to improve the parallelism. In our experiment, we are using 16 PEs. So of course, we also have some hardware-specific optimizations. For example, of course, because we are using FPGA, we don't like divisions and we don't like floating points. So we're replacing the initial values, 1 and 0s in the PPR vector using large enough fixed point integers. We're also trying to reduce data transfer. Because we only need these top K nodes, we don't need to store the entire global score table, but we can only keep a size of C times K. And in the experiment, we observed that if C is larger than 8 or 10, there is no precision loss. So we let C equals 10 in the experiment. So now here comes the final experiment. We implemented the algorithm using Python on CPU and implement the accelerator on Xilinx Kintex. The baseline is the naive PPR by loading the entire subgraph of length large L. Okay, now here comes the final experiment. We implemented the proposed algorithm using Python on CPU and also implement the PPR accelerator on Xilinx. The baseline is the naive PPR by loading the entire subgraph of size L, large L. And this figure demonstrates the memory reduction. We can notice that MeLoPPR on CPU can achieve 1.5 to 13.4 times reduction on average. This is because of the smaller subgraph we expected. And on FPGA, the reduction is more significant from more than 70 times to more than 7,000 times reduction on average. This is because of the FPGA's customized storage system that eliminates all the redundancy. Of course, here we have to admit that part of the reason is Python occupies a large memory because of its data structure. So in the future, we will do a better job to compare here. And in addition to memory reduction, let's see the trade-offs between latency and precision. So as we discussed earlier, we don't compute all the nodes with non-zero values, but instead we only selectively compute a portion of it. So apparently the more nodes we compute, the higher precision we get. If we compute all of them, of course, we will definitely get a precision 1.0. So if we choose the number of nodes to be computed, we can control the latency and precision trade-off. And in this figure, there are 6 realistic benchmarks. And the yellow bars are the CPU speed up over baseline, and the gray bars are the FPGA baseline, the FPGA speed up. And we can clearly see that there is a curve between the accuracy and the speed up. So the precision increases while the speed up decreases. We can see that sometimes CPU can achieve around 90% precision, but still with a speed up. For example, this Amazon example and this DDLP example, that it can achieve 90% precision, but still with a CPU speed up. And on the other hand, for the FPGA implementation, it is always achieving speed up while the precision is approaching 90%. For example, from this 3 times speed up to the 70 times speed up. So this apparently demonstrates that FPGA accelerator is absolutely necessary. But of course, in the future, we will do a better comparison by using the C implementation as a baseline. So this is all about this work. To briefly conclude, we discussed a memory-efficient, low-latency, personalized PageRank algorithm, which is achieved through stage decomposition, linear decomposition, and PPR vector sparsity. We also demonstrated the CPU memory reduction with a flexible latency and precision trade-off, and we also discussed an FPGA accelerator. On the other hand, there are actually a lot of future works that can be done based on this proposed idea. So one straightforward extension is that we can parallelize the subgraph computation, and I'm pretty sure that it can easily beat the current baseline because there is no dependency between different subgraphs, and this is very friendly for parallel computation. So if you are interested, please take this and try to beat us. And the second is we have to discuss the scalability for more stages. What if we decompose it into 3 or 4 or 5 different stages? It can still be very challenging to reduce the overall latency. Okay, so this is the end of this presentation, and thank you very much for listening. If you have any questions, please feel free to reach out at sharklab@Georgia Tech. Thank you very much.